So if we do this, yeah, there it is. So now let's see what. Nice. Okay. Hello everyone, and welcome back to another episode of One Day Exploit Development. In this video, we will look at a vulnerability in something called Squirrel. This is a language engine, and this is actually a pretty old vulnerability back in 2021. But it is one of my favorites, and I never developed an exploit for it, so I thought it's worth making a video about it. One of the interesting things is that they wrote, like, those researchers, they found the vulnerability and wrote the write-up, but they never shared the exploit. So we are going to write our own exploit today using the bug details. Okay, so a small intro about Squirrel. This is like a language. Squirrel is an interpreted open source programming language that is used by video games and cloud services for customization and plugin development. That's basically it. It's like a language engine that you embed inside your game or your server, and it allows you to create like custom modes and custom maps and stuff like that. And popular games like CSGO use it, and other games. Yeah, and here like they describe the risk. This comes with a price. Anyone who downloads and hosts such an item from the community executes Squirrel code without any warning. Some of the most popular community-created items have been downloaded millions of times in the popular Steam shop. In order to prevent malicious actors from exploiting this, the Squirrel engine is carefully sandboxed within the CSGO process. In this blog post, we will break down a vulnerability we discovered in the core of Squirrel, which was developed in C. It enables an attacker to bypass the sandbox restrictions and execute arbitrary code within the Squirrel virtual machine, giving the attacker full access to the underlying machine. So they basically found a vulnerability within the implementation of the language, which I really like. Some of you who know me knows that I love language interpreters and bugs and sandboxes and escaping sandboxes. So this is what we're gonna do in this video. Now let me think. Is there anything else we should cover before starting? And also, like, I just collected information about the bug and the engine and the code base and stuff like that, and how to get the sources. And I also compiled it, mess around with it. I also tried to run the POC that they provided. Where is it? Somewhere down here. Yeah, the POC, and it crashed, which was very nice, but I didn't go any further with that. This is what we're going to do in the video. Okay, so I think the first step would be to build this. So I already built it, but I ran make clean just to have a fresh start when I record this video. So Yeah. And like bin, SQO. Yeah, and then you have, this is the language engine in action. You can also see like version, no, oops, it's just V. Right. And if we run their POC, you will see the crash. It takes time because there's a loop here. Oh no, actually they have like a special, they have a funny extension for their file. It's called nut. And yeah, you can see our segmentation followed now. We can also debug it just to see the how did they say? It's a null pointer dereference here. This code gives you a null pointer deref. Segfault. Right. So set args. Right. But I don't like that. I want it to be, it's not good. I want debug. Debug info. 1 second. How do they? Yep, there it is. Come on. Where is it? C flags. No. What? Let me see. Bin. Squirrel. Squirrel. Okay. Defs. Oh. Okay. So. Okay. Now let's. What? Set args. No. I just want to add debug info. Why is that so? Damn. Okay, you know what? Let's Let's try to do it like... Well, first of all, I gotta clean the bin. And then make C flags. No! Okay. And G3. Okay. No, I don't think it... Okay, I think it's just defs. Let's do some makefile hacking and where is it? Okay, let's now try to GTP. No. Defs. Man, I feel stupid right now. SQ. You know what? Let's try to use the makefile, the C makefile. Make clean. Material build. CD build. CMake. Okay. C flags. How do you like? Oh. CMake. Come on. Good. This is stupid. Very, very stupid. Let's see, my compiler is slow. So you do that. Thank you. D. Where is it? B built and the SQ flags G3. Does that make sense? Okay. And like GDB. CD. CA. Alright. And then you have build makefile. Yeah. Okay. Release. Oh, I can't. I have to. 38. Okay. SQ build type debug release. Okay. This is what I want. And release G3. Okay. Okay. Now make their build and then go build and do CMake. And CMake compile commands JSON. There it is. Okay, so now what? CMake. Oh, no. It's like that, I think. Yeah. No. Okay. Build. How to generate. Yeah. I did it. CMake export. Oh, no. It should be CMake. There it is. Nice. Now we'll have no, that's not good. Nope. Maybe maybe now. That's fucking weird. Release. And what do you want? Oh, I see. Okay. So I need to do CMake CXX flags and then G3. Yeah, I need to do it on a fresh build, so. Now it should work. Now it should work. Build and this. Nice. Nice. Very good. Cool. So now we are ready. GDP. No, maybe I should do it in another window. GDP build SQ set args. Okay, we have source code. Wow, that was disgusting. Okay, so now let's see where the crash is with debug info. Yeah, and just like the blog post said, we are crashing in a null pointer, dref. Where is it? Null pointer dref. Now that we have the interpreter compiled with debug info, and we managed to reproduce the crash, and we have compilation database, so it's easier to navigate in the source code. Command D. Let's just set this up. Settings, workspace, compile, commands here. Build. Yep. Okay, so we can go, I don't know, like here. Yeah, and we have debug info. Like we can cross-reference stuff, and yep, it's very nice. So now we have all the setup ready. Yeah, now we can take a look at the bug. Let me just exit. So the bug is, but before we get to the bug, let's look at how several before we get to look at the bug, let's look at how Squirrel objects are laid out in memory. So as the blog author here shows, you can have classes in Squirrel, and just like any other language, like or object-oriented language, and this class can have fields and methods, and in memory, every class that you define will look like that. This class in Squirrel will have a SQ class object with two class members. One of them is default values and the other one is methods. Each one of them is a pointer, and it points to another heap chunk that is just an array filled with something called SQValues or SQObjects, as you can see here. The above image shows Squirrel class definition contains a pointer to a dynamic array of methods in which some method would be stored. And he's referring to this some method. As well as a pointer to a dynamic array of default values, both first field and second field, along with their default values will be stored there. And when he said default values, he means that. Now, in order to access these default values and methods, SQ class definition also contains a pointer to a hash map. which is members. Now, the bug in this blog post is that every time you access an index inside a class object, you can set index and get indexes using raw get and raw set. So every time you access index, there is a check that happens in the background. And this check verifies if one of the bits is set, and I'll show you. Following code snippet shows a new slot, which is called index is stored. What I wanted to show you was that every time you access something in a class, like if you want to access a field or a method, you have to specify an index. And as he described here, he says that in order to access these default values and methods, an SQ class definition also contains a pointer to a hash map. Hash map members maps the name of the attributes to their index within either the default values or methods array. And in order to determine if the index should be used to access methods or default values, a bit flag within the index is used. The following code snippet shows a call to members new slot, which adds a new slot. Adds a new slot like when a member is defined. And you can see that it just taking default values and, no, I'm sorry, it takes members and then add. This is me from the future. I just wanted to provide a better explanation because the one I recorded originally wasn't clear enough. So let's take this example class in Squirrel. First, an SQ class object is created. Then a new class member is defined. And the declaration of a new class member is done in two parts. First, we push the new value into the members hash map. This value will contain two important things. The first thing is the type information. Is this a field? Is this a method? And the second part of information will be the index that the value is stored in the default values array, because the default values array, this is where all the actual values are stored. And then in the second operation, we actually push the value to the default values array. So you have two things here. The first thing is the underscore members, which is a hash map that contains type information and the index of which you will find the value in underscore default values. So that was important to clarify. And the vulnerability lies in the fact that they define indexes and type information in the same integer, like in the same memory address, in the same variable, whatever you'd like to call it. And he also mentioned that here, the fact that bit flags are set within indexes is problematic, as it is entirely possible for an attacker to create a class definition with 0x 2 million methods, as such we create in a very simple POC. So what he did, he created an empty class with no fields, and just ran a loop that runs 2,000,008 times to add 2,000,008 class attributes or class members, whatever you like to call it. And then after he filled the class with a lot of methods, and keep in mind that there are no fields in this class, only methods. After he filled this with 0x to 1,000,008 methods, he tries to access the index number 0x to 1,000,004. Now, what will happen is that this. It will check the type, whether it's field. If it's field, it will remove this byte and just keep all that. And this way it will access the index. And if it's a method, it will do the same, but for the methods array. And specifically, the issue here is with this macro. And he also mentioned that here. The isField macro returns true if the bit flag 0x to 1,000,000 is set in the index. The bug lies in the fact that an attacker that is able to insert at least 0x to 1,000,000 methods into a class definition can force this check to return true, since the bit flag would be set. To make this more concrete, and then he gives like an attack scenario, which is basically this, the description of this POC. He created a class definition with 2,000,005 methods and just one field, and then he tries to access the method with a corresponding index of 2,000,005. The isField macro will detect that this bit is set, so it will like hit this, and then it will go here and not into that part, which it's supposed to go to here, but it will go here. And this macro will remove this, the member IDX. You see, it removes in the 0x to 1,000,004, it will remove the 2. So what you will have here is just here's the number 4. And obviously this is out of bound because you just have one field. You don't have 4. So this is how you access outside of the default values boundaries. And yeah, he just says here what we just said. This will macro return true, and then the default value array is accessed within the index of 5. However, it only contains 1 entries, and thus the attacker has accessed out of bounds. Yeah, okay, so in terms of what we need to do, we already did this, we did this, we did this, and we also reproduced the crash. Now, we can fix the crash. It's not really fixing, like avoiding the crash. He says that it is crashing in a dereference null pointer because the default values array has not been allocated yet. Right. So we right, maybe that should work. Now the default values should be allocated. So it's going to access out of bound. I hope. Build SQ. Right. Sorry. Oh, I forgot. Now let's see. Cool. That looks abnormal. Now let's try to, you know, say 100, right? And this should be 100 too. And then print. Now let's see. It should print a lot of leaks. Oh no. Okay. Cooking. Print. And then we would have here leaking vowels. All right. Line 6. That's weird. As long as I is smaller than. It doesn't make a difference. But let's try it like that. No. Okay, you know what? Maybe I was too. Let's try that. Why? It's not printing anything. Doesn't make sense. Two. 1, 2, 3. 1, 2, 3. 1, 2, 3. One, two, three. So that's like, I don't know what to say. It's just 8. Just 8. Nothing more. Just 8. Okay. Okay. Perfect. Now, that looks like a bunch of leaks. Why is it like that? Okay. Whew, finally. Okay, so we do have out of bounds. I mean, in the first iteration, it's not yet, but like, oh, actually it is. Yeah. Okay, so now we know that we can. Maybe. Okay, so we're not crashing anymore. And we managed to have out of bound access. That's nice. But we want more than that. We want out of bound read write and like heap spraying. He also mentioned it here. He said that like it's pretty trivial. It's pretty common to use this technique of object pointer that points to null and with a lot of entries, and then you can access all the memory space. The annoying part is this. Through careful preparation of the heap, it is possible to craft a string that imitates a very long string or a very long array. Okay, so let's carefully prepare the heap. Okay, so the next step would be to craft a fakeObj primitive. This should be in our dictionary. We can do it by spray. For I. I'll just try to be naive with this approach. Just spray a lot of strings. And then we can do spray. Yeah. Build. That's pretty weird. Okay, let's debug it. Set args x.math. gdb. And then break at break. Oh shit. I forgot to save the stack trace. Raw get. And then do this. Run. Oh, no shit. I forgot. Okay. Now it should crash. Because this is not defined. I can keep it here. And get and raw get and right. So it sees that you're trying to get from a class. And then, whoa, well, everything is red. Just take that. Where were we? Over here. Right, and then I'm just doing this to have like less errors when I reference stuff. So back to where we were earlier, that's here. We're in get. And get, take default values. Default values is not allocated yet, so can we print it? Members. Yeah, it's not allocated yet. So we should break here. I want to break here. Yep. Now we run this. Print obj. Yeah, that's that's the index. And self is the class, I think. Yep, class. So if we do self dot underscore p class, because this is a class. Oh, that's not it. We can see default values, and now default values is allocated because we set one member here. So every time we try to okay. So what is the distance? Like 0x 3e8. So we should be doing, let's get rid of that loop and instead just print one value, which would be 125. Or no, it shouldn't be. It should be like, what is it? P-type. Default values. Where is default values? Oh, this is default values. So it's a class member or SQ vector. Let me see it in the source code. Default values. Yeah. Oh, this type is like an SQ vector of class member. And class member is this. It's an object pointer. Okay. So the size of this thing would be class member 0x20. So you should divide it by 0x20. 32. Let's see. 32. Or even 33. It should land. Now what I'm doing is I'm accessing 33 SQ members outside of the default values array. Each element of the default values array has a size of 0x20. So we need to access the 31 or 32 index or the 32 element in order to reach that memory area. And then we'll touch a fake object that the contents of this object is controlled by us. Thus, we will get a fakeObj primitive. That's pretty naive, but let's see if that works. And if we are doing print default values, 33. What? 33. Okay. So now let's see what it's going to print. Nice. Okay. Pretty nice. But is this going to work with? I'm not sure it's reliable enough. Like what happens if we do 0x Let's try to fake string or something. How do I get and then a string? Because we have a breakpoint on raw get, because we have a breakpoint on raw get, we will see this value in memory, like how it's represented in memory. It's obj, right? And this is a string, this is the string, and if we inspect that value, pString, we can see that it has a 0x13 length, and what is this shared data? Shared data. Oh, shared state. No, I don't want shared state. I want, oh, val. There it is. It's like the t is this t. So if we hex dump this, we will see. Yep, this is a test string. So the layout of this object is like that. The first thing is just a pointer to, I don't know, a destructor. And then you will have the type. I think string is a type. Let's see. String. No, it's 0x10. Okay. So what is the layout of ptype? No. Yeah, okay. So the first thing is a pointer to a shared state, and then next, and then, oh, but it extends ref counted. So let's see, ref counted. Oh, no, we don't want to fake a string. We want to fake an object that points to a string. That's what we want to fake. That is what we want to fake. Where is this structure? SQObjectPtr. Oh, the first field. No, the first field is SQObject type. Yep. This is a tagged object. So the type is string. We need to hex dump obj. That's what we need to. Right. So you have 8 and 10, which makes sense because OT string is 8 and 10. This is the type, followed by the pointer, right? Which is the value. This is just a bunch of pointers. Okay. So we can spray. Zero x down, zeros. This is like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, and 1, 2, 3. That's going to be 8. One, 2, 3, 4, 5, 6, 7, 8. No, that's bad. I knew that would happen. Where is it? Okay, it's here. It's like BBB. Followed by the type. Telescope. Here it is. Yeah, now they have a different offset. This is gonna be nasty. Ugh. Okay. Oh, 36. So 37. Let's see how that. Oh. No, that's not good. No. That's not good. Four, 1, 2, 3, 4. And 37. Okay, now that looks better because we have a string that points to 424242, and we are trying to print it, and it's going to segfault because this address doesn't exist. Let's see. Okay, that's a fail. That's a major fail. Why is that? $37. Maybe we should. Oh shit! Maybe we should make 36. Let's see it. Okay, maybe I should have done it. 36 and not 37. $36 is OT string. That has an address of 42. IR. Cool. Yeah, I can also see it here. So, very cool. Now, we can craft a fakeObj. But we need to know. We need to know what we want to read. I think that I think it's possible to. They print addresses. They are very generous with their output. So maybe if we print a function, it would give us a heap leak. I previously did this in like Lua, I think. Xerix. Oh no. I have a new domain. I forgot about that. Where is it? Lua. Or Heap. Leak. Yeah, you can see in many languages, if you print a function, or if you print a table, or an array or whatever, it will give you the address. So maybe this is also relevant here. Print. Yeah. Yep. Pretty cool. Okay. So our next task would be get a valid heap address. And we can. Okay, we need to fix that. This is a mess. Okay. Let's add it here in the beginning. this is the output. So this is the output, and we want to extract it. So it's like 0x 0 to 9, A to F. Yep. Nope. Why is this? Okay. And then, how do you pronounce squirrel? I always have typos. Squirrel docs string regex. This is what I want. Capture. And then use slice. Oh, it's very similar to Lua, like a lot of the syntax and the functions. And they even have, no, they don't. Pretty sure I saw this somewhere, to string. Okay, let's just stay on topic. I'm sorry. Yeah. So we want, not def, this is not Python. Function, get heap address. And then, leak. Print to string. Print no leak. Get heap address. Let's see it. Yes, still works. Okay, and then once we have this string, we want to apply the regex that we built. How does it do it? X local x equals regex, and that regex. And then capture. No, we already have string, so local s next search. I don't know what the difference, but search looks easier and more compact. OX search. Well, and print grabbed str String slice res begin res end. How do you say it? Squirrel to integer. Yes. To integer. Come on. Yes, you can provide a base. So string to integer, and then 16. Yeah. Print Heap header is print oh, that's weird. Maybe I should grab this str. String doesn't exist. No. Slice. String dot slice. What is it? String dot slice. Table index string does not exist. On line 8. The fuck? String. What? They don't have string? No. Come on. Don't be stupid. Test. Okay. So we do have string dot slice res begin something's odd here. No, this is like, it's gonna be a stupid syntax error. Okay, let's just copy and paste string.slice. No, we already have it. Maybe it's this. Oh my god. To integer 16. I don't know, like 3. No leak. This print. Maybe few. I don't know. This is a weird language. The index string does not exist on line 8 and 15. So it's like 8. Search, no leak, and regex. Let's see it. Okay. Okay. Good. So, that's like, yep, it's this address. Returns the address of the rescue object that points heap that points to print. Right, and this is the class. This is triggering the bug, and then okay. So if we paste those bytes here, I think I need to take a break. It's been another hour already. Okay, I'm back now. I was thinking about it, and if we will continue with this approach of spraying strings, we will need another function that's like converting a number into bytes and then pasting it here. And I don't know if I want that. Maybe we can spray something else. Maybe tables. I think I saw this somewhere here. Oh, there it is. Yes, I knew it. Squirrel API. Okay. You can create a blob object and choose a size, which I think it's better than like concatenating a string. Okay. So what is run? Okay. Let's vals here. It has a size of 0x90. Okay. Let's bring that here. And we want to change the spray. To blob 0x90. And then how do you fill this? You have seek. You have write and write n. I like that. Okay. Let's write n. Let's do this. C, because C are 8 bits. Or maybe B. And blob size. We can do it like that. And just for debug purposes, I will write this line because I have a breakpoint on because I have a breakpoint on raw get, and I want to see how that blob object is laid out in memory. Yeah. Print self, and then no obj. Yes, this is an instance. Like user instance, user pointer, SQ user pointer. What's that? No, this is a void pointer. What points to? Blob set squirrel blob self get user pointer SQBlob, and then print. Now dereference that. That's a little bit weird. But okay, that looks good. And the size is 0x890. So right, it's here. Okay. What is the distance between this Is this a reasonable distance? Print self. And then p class default values. No, that's too far. Where is it? Heap chunk. Xerox90. And this also Xerox90. Oh. I think I know. It's not really Xerox90. It's Xerox90 from the perspective of Squirrel engine, but what? No, that's not. What? No. Just continue. Okay. Now it shows the size. I don't know what happened earlier, but okay, so the size is too big. We need to make it 0x90. And that's A0. So I think we need to, this would be 90. Yeah. Because of the header, extra bytes. Okay, now if they are the same size, maybe it would be, maybe they will be closer. Let's say heap chunk. Yeah, now it's 0x90. And if we look at this is also 0x90. No? Oh my god. Why? No, that's too far now. Shit. No, that's not good. 0x90. Spray. No. Yeah, I need to. Maybe if we like allocate it more, maybe then it will be more deterministic. Okay. Malloc. And then malloc is malloc. Okay, so that's triggering, that's spraying, and you spray, and then... Oh, I know what. Or, no, maybe... Yeah, it's in the right place. Should we, like... do that? I'm just creating a lot of blobs. Hopefully this will make it more more predictable. Okay. Print. Wait, is that? Smaller? No, it's not. Oh, thank God. Okay, so what is the distance? There is no fucking way. What? This and this is itself. This is obj. What? Then where is it? No way. This. Oh yeah, so it's behind. It's behind. Not good. Not good. So if we do this, yeah, there it is. And then our vowels is like literally here. Fuck. How is that even possible? Okay, if we don't do that, what happens? And then user pointer. It's still before. It's still before. That's pretty bad. Why? We should put it after. Maybe because this function, maybe it caused a free or something. Let's see if we comment that out. Let me do run. Okay. Let me see. Maybe the size should be. I think I made a mistake with my calculation earlier. And that's 7710. That's 77D0. Still not good. This is bigger than this. Blob size is this. Take blob size, you allocate it, you take it, and then you write, you fill it with A. What if you do this? Maybe because we are referencing the pawnable class during the compiling phase. It's like changing the order of allocations. I don't know, it's just, that's the wild guess. fakeObj. No, like buff. Yeah. Okay. No, that's I think that's good. No. Why? Maybe it's something with the raw get. What? You know what? Okay, what happens if we allocate 200? Maybe the size is not common. And then you do files. User pointer. That's 7820. That's definitely bigger. Now we will see the AAA. No? Oh my god, what? What is the distance? No, fuck. Doesn't make sense. Thank God. That's not good because it's too far. I don't want it to be so far. Yeah, here it is. But there's a lot of garbage in between. Okay, so we're 90. Buff. What do you mean? Oh, okay. No, that's not what I want. Yeah, okay, like that. So this is buff, and then you have vals. So I want to see distance between buff. Come on. This is stupid. Never mind. That's buff, and that's vals. C0, that's good. Okay. So if, wait, what? No, not again. Not again. Okay, let's see. Oh, my God, stupid. You know what? I think I know. Resize. Let's move that bullshit. And then red resize. X 90. Or maybe we can even resize to the same size. Let's see if that reallocates it. No, it's not. Okay. It's 20. It's still smaller. Yep. Oh, what? That's not smaller. No, that's not bigger. It's not bigger, so. Yeah. Yeah, that's not good. What if you change it? What if you change it to something smaller? What happens next? Okay, I think now, finally, that's okay. That's for. I'm starting to regret that I did all this. And red val, and red val is blob. Okay. Is this after? Nope, that's still before. Move it to 0. I want that. Now it's going to be faster. Mm-hmm. Ten 29. Good. Now we're gonna do as no. We need obj. Okay. There should be more AAA here somewhere. Okay. Oh, just one. So it's not spraying. It's not spraying. Okay, how do you use this table? Spray table. Spray table. J. Like that. Mm-hmm. Okay. Mm-hmm. Oh, now we are spraying objects. Now we're spraying objects. This is 1, 2, 3, 4, 5, 6. Cool. Very good. Horrible. Okay. Now we want to print this, and we want to print that. And we want to see what is the distance between this and that. Oh, that's a lot. Okay, it is a lot. This is a lot because we are spray then 0x. Let's make it 10. Not again. Come on. How? Okay, let's just increase the spray line. Is this the same? Like, what the fuck, man? That's 0x90. Good chunk. That's 0x90. Something doesn't add up. 40. Run. Like, how is that even? What's 5 pages? No. No fucking way. You know, I think I know what we need to do. Let's see, heap, shape, and we do this. Yeah. Now return spray table. All right, and we will call heap shape before we'll call heap shape before we are getting the fake buffer. Or no. Before we touch the class. It's buff, and that's vals. And now buff is bigger. Okay. Freeze it. Okay. Oh, I think it's free. It's like the engine see that we aren't using it, so he's freeing it. Okay. Oh, I can see them. Well, you know what? Fine. I don't care anymore. I don't care anymore. Let's just stick with the maybe we just need to use uncommon size, like 030 zeros. Small bins. That's the Tcache. We don't want Tcache. Yeah. So it belongs to the Xerox90. Is that like Xerox90? Oh, need to have. Oh, that's weird. What? Oh, what is this? How do you? Wardrobe. Okay. I think that's the issue. We need to empty. We need to empty that bin because it's in a very early addresses. 5 and 7. Okay, well that's take this spray table. Yep. Now, let's see. Buff. Buff. What? Thank you. Heap bins. tcache. Count 1. Okay, that's almost. Is this something that we use or? Yeah. Okay. So 50 and 50. I want them to be empty. Tcache for 0x90, just 1. Okay. I don't know why, but I guess. Buff. Why it's not. It's brilliant. That's going to be J. And J. We'll write that. Oh, shit. Oh. Yeah, now the tcache is empty for 0x90, right? Yeah, you don't have it. Okay. That's buff and that's vals. Now we're going to see the distance. Okay, it's getting better. This is 7140. This is 2160. And Heap is tcache. Tcache is still empty. Okay, now it's getting dangerous. Okay, no tcache. No, that's not good. So Hmm. Still not good. What happened? Still not good. Yeah, we need to get it back to 20. That's what we need to do. And then bounce. Okay, just take it 305. 305. $305. Cool. And 4 and 6. Okay. Now to continue. And that index does not exist because we need to make this bigger. What? Oh, I'm sorry. Good. Wow, that was disgusting. Okay. Okay. Now just fake buff seek 0 and then fake so buff right I. This is a byte. $57. Uh-oh. Uh-oh. That's the wrong. Maybe 306. Seven. No, that's not good. 4. That's not good. That's not good. Should be 1, 2, 3, 4. Yeah. Until we reach 0x 80. Okay. And the distance between above the levels. I don't like that. I don't like that. 345. Okay. 345. Okay, that looks better, finally. So yeah, it's like so 48, 49. And no, is it? Maybe it should be 4. Yeah. And that's 28. So now we can do fakeObj seek 0x 28, and then fakeObj right n 0x41b 2, 3, 4. Oh shit, I'm sorry. That's not good. One more time. Nope. But we said 28. Fire. Yep, that's not good. It's not good. Okay, small update. I just pressed Control C until I got to the previous version before we started messing around with the bytes object, like blob object, because I don't know, I felt like it's consumed too much energy, and maybe it's better to stay with this Spring approach, which was surprisingly accurate. Like, this is very close to the default values array, unlike the previous unlike the last approach that I tried with a blob object. That was very far, and just it changed the locations of the object between each run, and it made the exploit unpredictable. So yeah, I just Control Z until we came back here. I don't know if I'm going to continue to work on it today, because I'm very tired. That thing was what now? What now? Maybe more Control Z? No, that's where we stopped. We stopped here. Okay. I'm too tired. Fuck that. Okay, this is just an update to report that I managed to fix the heap layout. Now, this is really close to the default values array. Like the buffer that we are allocating, the blob, is really close to the class members. So that's good. And as you can see here, I'm accessing offset 0x28, and then I'm starting to write bytes, and that comes out to be that value. That's like 41, 42, 43, and then 90, 90, 90, because we are filling this buffer with a lot of 0x90. So now that works. I think the issue was with this function, because let me show you. If you uncomment that, the entire exploit melts into itself, you see? And this is because we are defining a new function. So it's probably create another, I don't know, like another function object or whatever. But if we are making this part of the main logic, so we can get everything working, like even the leak and our fakeObj. So we can just, this is not spray, this is get buff. And what? And this is buff. No. Yeah, okay, buff. And okay. I can remove this. Yeah, and it still works. Cool. Very cool.